This is a brief summary of a new paper that just came out called Increased Exposure of Coastal Cities to Sea Level Rise Due to Internal Climate Variability. Internal climate variability is something we discussed before, but just to briefly mention again, these are the internal modes of variability like El Nino, La Nina, North Atlantic Oscillation, Atlantic multi-decadal oscillations. So you have an alphabet soup of modes of climate variability like ENSO, NAO, AMO, PDO, PDV, IPO, etc., etc. And these are obviously generated internally within the climate system, not from changes in the external forcing from the sun or external forcing from greenhouse gases. These tend to control sea level variability at multiple time scales, literally from days to weeks and decades. And the decadal variability of sea level rise can confound the trends resulting from external forcing or due to anthropogenic greenhouse gas increases, which result in ocean warming, and the steric rise versus glacier melts and eustatic rise from those waters being released onto the ocean. So let's start by reading the abstract. Why revisit this at this point? Internal variability is hard to estimate, especially going into the future, but there are now new runs called large ensembles where multiple realizations of future scenarios are made by many of these models, and large ensembles give you a much better handle on the statistics of internal variability, because you need to know how many potential pathways there are that the climate system can take without changing the external forcing. And you have to also then take the past, for example, the 1900s, and see whether you can estimate the internal variability from historic observations to see how the models are capturing this internal variability in the large ensembles. So there is a lot of statistics involved, a lot of interpretations involved. The main thing to remember is that these models still do not have necessarily the contributions from glacier melts into sea level rise, and of course the tectonic movements which are part of either glacial melt and isostatic rebounds, or general continental movements that occur naturally as well. So we have to keep in mind that there are uncertainties, but nonetheless within all these constraints we can understand if there are regions where internal climate variability contributes a large amount to the sea level rise and exacerbate the risks of some of the coastal cities. Okay, adaptation to future sea level rise is based on projections of continuously improving climate models. Well, this is a statement that you have to judge for yourself, because if you look at comparisons between CMIP 3, CMIP 5, CMIP 6, whether there is really continuous improvement is subject to interpretation. These projections are accompanied by inherent uncertainties, including those due to internal climate variability. The ICV rises from a complex and unpredictable interactions within and between climate system components, rendering its impacts irreducible, in the sense that these uncertainties from internal variability cannot be really wished away or reduced by improving the models. They are just intrinsic to the system. So if your signal is looking for anthropogenic influence on sea level rise, then internal variability is the noise, and it's naturally occurring noise, so you cannot get rid of it. So you have to just estimate it and then worry about what it does to sea level rise in this case. Although neglecting this uncertainty can lead to an underestimation of future sea level rise, its estimation and impacts have not been fully explored for various reasons. Combining the Community Earth System Model version 1 large ensemble experiments with power loss statistics, we show that by 2100, if the internal climate variability uncertainty reaches its upper limit, new sea level rise hotspots would appear in Southeast Asian megacities like Chennai, Kolkata, Yangon, Bangkok, Ho Chi Minh City, and Manila, which are all global south highly vulnerable cities with very heavy density of populations very close to sea level. In the Western Pacific islands, which are also highly vulnerable, and the Western Indian Ocean, again highly vulnerable countries. The better the ICV uncertainty is taken into account and correctly estimated, the more effective adaptation strategies can be elaborated with confidence and actions to follow. So the Community Earth System model is from NCAR, the National Center for Atmospheric Research, which has been doing community models for a long time. Used to be Community Climate System, now it's Community Earth System model, and so on and so forth. So here we are looking at scaling exponents alpha of stereodynamic sea level fluctuations. The top figure we'll go back to is estimated from 1800 year CSM1 pre-industrial control run by DFA, which is Detrended Fluctuation Analysis 3 statistical method, with windows of sizes ranging from 1 to 95 years. So there are multiple time scales in sea levels which have to be considered for spectral estimates of scaling exponents. For uncorrelated data, alpha is 0.5, so white noise, which means it's an uncorrelated noise that is internal variability. And for long-term correlated data, alpha is greater than 0.5, which means the sea level rise or variability due to internal variability of the ocean, advection, strong currents, advection of heat, strong currents that persist for a long time, add to low frequency sea level rise, which can be confused or can add to the anthropogenic trend. So you have to understand how much of this is forced versus how much of it is natural, because natural means it goes up and down at some time scale, for example. Okay. So we are looking here at uncorrelated noise. This alpha comes from a statistical power spectral analysis that is done here to fit all these time scales, 1 to 95 year in this case, to see how the sea level from the model varies and what are the regions which are the regions where the uncertainty is lower. So uncorrelated noise is at alpha of 0.5. You can look up the equation in the paper. It's not that critical, but what is critical is to understand that the physics, the dynamics of the oceans are such that there are regions where there are strong currents, like the western boundary currents extending into the open ocean, here the Gulf Stream, the Kuroshio, and there are other regions with various physics of the ocean, dynamics of the ocean, that contribute to higher uncertainty with their long-term correlation, and we have to worry about these when we want to interpret the future sea level rise risks for many of the coastal regions. So here again in the second one, we are looking at the top view, looking at the Arctic here and the Antarctic. And Southern Ocean is always special. It's an open channel, so it has where it can absorb a lot of the wind energy, because wind can churn the ocean continuously here, as opposed to in lower latitudes where there are boundaries to the ocean and the wind energy is limited. So the dynamics of that becomes very important as well. So this gives you a sense of where the uncertainty is low with uncorrelated white noise, and where the uncertainty is high with colored noise or red noise spectra that add to the signal that one has to be careful about. Okay, geographical distribution of the internal climate variability uncertainty range of stereodynamics. So steric is where water temperatures increase or density changes, molecular arrangements change, and then the volume changes, so sea level changes. And dynamic is where the advection and circulations move the heat content around and create dynamic sea level variabilities and trends, and so on. So this is looking at stereodynamic sea level changes by 2005 relative to 1920. So this is to make sure that the model is capturing in some sense the historic internal variability. So this is A and B are estimated from power law statistics, so two-sided. There are some details on how this works. Basically, it is to see in the large ensemble, you can just look at the ensemble members and the standard deviations between them, for example, as a measure of internal variability related to multiple realizations of the model. But you can also take these and fit a power law curve to see if the two are matched to each other in a reasonable way. And you can see here the map again of the internal climate variability from power law in terms of uncertainty in centimeters, where there are places where the uncertainties are very low, and there are regions where there are coherent currents and movement of heat, etc., like the Kuroshio, again the north equatorial current here, I suspect that's what this is, the Gulf Stream here, and so on, where the uncertainties due to internal climate variability from power law are high in terms of centimeters, and from the model estimated uncertainty there is a good match between the two, so you get some kind of confirmation that the model is doing reasonably well. So if you look at ICV power law versus ICV from the model, you can see that in some regions the correlations are high, but there are regions like the Pacific intertropical region here where the spread between the two is very high, and there are other regions as well in the Pacific intertropical in the southern hemisphere and in the South Indian Ocean and the North Indian Ocean. So these are regions where the contributions from internal variability has to be watched out for very carefully. So I'm being very brief, but you can go and see. The main point is I want to convey is that internal climate variability is going to be important to worry about when it comes to its contribution to sea level and estimating the risks to coastal megacities, for example, and what to do with those future projections of sea level is not always clear. Do people really move away from the coast based on these projections? Or if you want to build protection against these estimated sea level rises, then it's not that if the sea level rise projected is 1 meter, then you will protect against 1 meter, because it depends on how much that will cost. So many communities, for example in the northeast US or in Europe, are already spending money on protecting against sea level rise, but they determine that based on how much it costs. So even if the projection is 1 meter, they may only be able to protect against 50 centimeter rise, for example. Okay, so we have to worry about all these sorts of things. This is showing the stereodynamic sea level rise by 2100 under one of the scenarios, RCP 8.5 relative to 2006. This is representative concentration pathway 8.5, where 8.5 watts per meter squared is the resulting radiative imbalance by 2100, which is the business as usual scenario, which will give us warming of 4 or 5 degrees or higher. So we are looking at maximum expected ICV contribution in centimeters, where there are places the contributions can be very high and there are places where the contributions are not that high. We'll see another map of this in a minute. This is the maximum expected sea level rise total, but before that look at just the externally forced sea level rise. So there are places where externally forced sea level rise is high, and the expected contribution from internal climate variability is also high. So some of these cities obviously are going to face a good combination of these contributions from internal climate variability as well as the anthropogenically forced component of sea level rise. Just keep those things in mind. Sorry, I got interrupted there. The final point to be made in this podcast is about the numbers for the coastal cities to look at. Upper bound scenario of the expected stereodynamic sea level rise by 2100 under the RCP 8.5 scenario relative to 2006. So these are the business as usual scenarios which produce the highest warming in the CMIP 5 AR5 assessment report 5 released in 2014. AR6, the assessment report 6, moved to so-called SSPs, or shared socioeconomic pathways, which combined the RCP 8.5 kind of number, where 8.5 is again the watts per meter squared energy imbalance by 2100, and then added 1, 2, 3, etc. for SSPs, which for example shared socioeconomic pathway 2, SSP2, is middle of the road. There are sustainabilities and other phase spaces that we used for SSPs that we looked at in another podcast that you can follow up. The other thing we keep in mind before we mention the numbers here is that the internal variability itself is going to be modulated, is already being modulated by the global warming. For example, the duration, intensity, and frequency of El Niños. We don't know exactly how they are changing or how they will change into the future. And there are many other modulations, multi-decadal variabilities like PDOs or AMOs also get modulated. Multi-decadal variability in the monsoon, for example, may be going from more like 20 to 30 years to maybe 50 to 60 years and so on. So all those things have to be kept in mind. Coming back to again sea level rise, you look at the various places. For example, let's zoom into the Indian Ocean region. So Karachi is going to expect by 2100 under this SSP2 pathway a sea level rise of 39 centimeters, with population expected to rise to 50 million by the projections used here. And you can see that the circle has mostly externally forced sea level with a bit of contribution from maximum expected internal climate variability. Similarly for Mumbai, a rise of 37 centimeters with population expected to rise to 58 million. Lots of uncertainties in the population projection, so one has to be careful. And it has a tiny bit of ICV contribution, whereas Chennai has a much higher contribution from internal climate variability with expected sea level rise of 42 centimeters and population jumping up to 22 million. Kolkata also has a fairly significant ICV contribution to sea level rise by 2100 under SSP2 with 44 centimeter sea level rise expected, and the population expected to top at 45 million. You can go down to here Ho Chi Minh, which has a fairly significant contribution from ICV as well, so 47 centimeter rise, population reaching 15 million, and so on. So you have to really worry about the global south countries like Mombasa here, 55 centimeter sea level rise expected with a huge contribution from internal climate variability, population reaching 11 million. These are really vulnerabilities that are dangerously high. Despite the uncertainties in the sea level and despite the uncertainties in what we can do about it, especially considering the sea level rise here is not caused by Mombasa or Kenya or these countries down here, but these are globally related to emissions since the Industrial Revolution, the melting of the glaciers, warming of the oceans, and so on and so forth. So all these things have to be considered, but it's good to have this estimate of internal climate variability from large ensemble simulations of the Community Earth System model of NCAR, and there will be many more such papers coming out on other aspects of internal variability contributions to the future and how they add up to the forced component of various things like extremes, not just sea level rise, but also cyclones and monsoon variability and extremes, trends, etc. Okay, so let me leave it here. Okay.